Hey, welcome. Today, we are going to pull back the curtain on one of the coolest and most useful algorithms out there for finding the best path from point A to point B. We're talking about the A-star search algorithm.
Have you ever really thought about how your GPS just works? I mean, you type in an address and boom, in seconds, it maps out the quickest way to get there even with traffic. Or how in a video game, an enemy character seems to find you no matter where you hide. How do they sort through all the possibilities so fast?
Well, the secret behind all that is a seriously brilliant algorithm called A-star search. That's pronounced A-star. It's this incredibly elegant solution that has become the absolute go-to for pathfinding problems pretty much everywhere.
So let's talk about where this thing actually shows up. You'd be surprised how often you interact with it without even realizing it.
A-star is pretty much the engine running under the hood of so much of our smart tech. It's in your GPS, obviously. It's how those robots in giant warehouses zip around without crashing into each other. It's the brain that lets a character in a game chase you through a complex level. It even helps route data across the internet. The goal in all of these is always the same: find the cheapest, most efficient path possible.
All right, so let's get into the nitty-gritty of what makes AR so special. Believe it or not, all of its power comes down to one single, really simple equation.
And this is it. This is the heart of the whole thing. The algorithm figures out how promising a path is by just adding two things together: the actual cost of the journey so far and a really smart guess about the cost for the rest of the way. Let's break that down. Think of it like you're on a road trip. The past cost, that's what you know for a fact. It's the miles you've already driven. The heuristic cost, that's your best guess. It's you looking at the map and saying, it looks like we've got about this far left to go.
Now here's the secret sauce. The heuristic, that guess, it has to be optimistic. It always has to underestimate the real cost, or at the very worst, be exactly right. A perfect example is just the straight line distance to your destination, as the crow flies. This little bit of optimism is what makes A-star so incredibly efficient and, as we're about to see, guarantees it finds the best path.
So, to manage all this information, A-star uses a couple of simple tools. You can think of it like a meticulous planner organizing a big project. Okay, so the algorithm basically has two lists to keep things straight. There's the open list, which is its to-do list. It's full of all the places it's thinking about visiting. Then there's the closed list, its done list, all the spots it has already checked out. And to make sure it doesn't get lost, it leaves a breadcrumb trail of parent links. So when it finally reaches the end, it can trace its steps all the way back to the start.
And here is the really clever part. That open list, the to-do list, isn't just a random jumble. It is always sorted, with the location that has the absolute lowest estimated total cost sitting right at the top. This is why A-star is what we call a best first search. It literally always explores what looks like the most promising option first.
So let's put it all together and actually watch this thing work. It's really just a simple loop that repeats over and over again.
So here's the process. A grabs the best-looking option from its to-do list. It moves that option over to the done list. Then it looks at all the immediate neighbors of that spot and asks each one, hey, is this a new, cheaper way to get to you? If the answer is yes, it updates that neighbor's info and plops it into the to-do list, right in the correctly sorted spot. And then it just repeats.
So imagine we're just starting. The only thing on our open list is our starting point. The cost to get there is 0 because we're already there. And let's just say our optimistic guess to the goal is 10. That gives us a total estimated cost of 10. Simple enough?
Okay, now we explore our starting point. We move it to the closed list and find it has two neighbors, A and B. We calculate the cost to get to each of them and their new estimated cost to the goal. And look at that. Neighbor A, with a total cost of 11, is now at the top of our list because it's cheaper than B's 13. So guess what? A-star is going to check out A next.
And this is where the magic really happens. Let's say we're a few steps later. After exploring A, we find a new spot, neighbor C. Now it costs more to get here, at past cost of 8, but look at its heuristic. It's super close to the goal, with a guess of only 2. That gives it a total estimated cost of 10, and that is better than B's 13. So C immediately jumps to the top of the to-do list. A-star just changed its mind, because C now looks like the most promising path forward.
So yeah, the process is clearly very smart, very efficient. But that brings us to the biggest, most important question of them all.
I mean, it's making guesses, right, with that heuristic thing? So how can we be 100% positive that it always finds the perfect path, and not just one that's, pretty good?
Well, the guarantee
The proof that it works perfectly comes down to two very simple conditions. First, that optimistic, always underestimating heuristic we keep talking about. And second, the fact that moving from one place to another always has a positive cost. You can't travel negative 10 feet, right?
So here's the key insight. Because our heuristic guess is always optimistic, that estimated total cost is basically a promise. It's a guarantee that the real final cost of any given path will be at least that number, and probably even higher.
And that leads to this beautiful conclusion. The moment A star picks the goal from the top of its to-do list, we know its cost is the real, actual final cost. And since every single other path still on that to-do list has an estimated cost that's already the same or higher, none of them could possibly end up being shorter. It's logically impossible. The first path it finds is guaranteed to be the best one, period.
So that's A star for you. It's this perfect mix of known information, the path so far, and a clever, optimistic guess about the future. And it just works, every single time. It really makes you think, right? If we have this incredible tool for teaching machines how to find the single best solution to a pathfinding problem, what other complex systems in our world are just waiting to be optimized?